Thank you for coming. My name is Meißner. I'm a master's student at Hasse-Plattner Institute in Potsdam in computer science. Yes, today is about my private project called Symatem, the symbol relation system, and an approach to software engineering in general, and just starting completely over again. Think about what we actually want to do, not what we are doing right now, and not trying to repaint the things we are doing, but rather unlearn what we have learned and reconstruct them completely. Okay, so first of all, if you have urgent questions because you're feeling that you're getting lost, raise your hand right away. If you think that's a discussion, postpone it to the end. And another thing, I mean, it's kind of sad that we have to do it in modern day, but everything I say here is just my opinion. This is a disclaimer. So please accept it the way it is, and please also challenge the preacher. Try to discuss things if you think that I'm doing mistakes and messing things up or something like that. Okay, so Symatem. First of all, what do we actually want in computing? I think there are 4 main domains, 3 more or less, depends on how you count them. One is the transport of information. So transport can mean transport in time or transport in space. So transport in time is storing things, transport in space is transmission. The next block is processing things, changing information. And the last block would be to kind of make an access point to the system, the tool chain, the user interfaces, and so on. So everything in my project is structured in this way. And of course there's the meta block of the project itself. This is also the timeline. So I will start with the transport, then the tool chain, the processing, the project. There will be some live demos and code in the middle. And also, at the end, there are some links for GitHub and so on. Okay, transport. So, the kind of question I ask myself in the beginning of the project is, what is information actually? Like, we do things with information all day, we program computers, but usually we don't think about information in the way we should do. So I encourage you to do a thought experiment, which I call the pen fence. And the pen fence is the following. You have somebody around the world which you write letters to. You don't speak to them in any other way. And one day both of you decide to buy 2 copies of exactly the same dictionary and index all the words from top to down, and then communicate only with the indices of these words, not the words themselves anymore. So what changes? Actually, nothing. Okay, you have a huge load of overhead of doing this, but the actual information stays the same. The symbols we use to encode information are completely irrelevant. So information is just the relation of symbols. And these relations make up the information. It's a graph. Of course, I'm only talking about discrete information here. Nothing like rational numbers, which in fact can also be represented if you have infinite amount of these relations. Okay. So, the idea is that all discrete information can be represented in so-called triples. These are 3 tuples of 3 symbols, and you see this happening all the time, like JSON, XML, natural languages, and even maths in binary relations. It's actually a trinary relation, because the relation itself is part of the triple. And if you can form information in this way, you can gain a unified way of finding a description for information in general. Of course, it has some downsides. So one question you can ask me right now is, why actually 3? Why not 2 or 4? So obviously 0 and 1 does not make any sense at all, like only having a symbol without a relation to anything else. 2 can be done, but it's a lot of proxies and just tries to emulate a higher number. And higher numbers than 3 usually have problems in defining a semantic for each position in the tuple all the time. Like, you have to do null values and schemes, and you have to define what a position should mean in a certain context. And if you try to do these, you usually end up, again, emulating 3, or the number of 3 tuples. That's what I learned over the course of my project. So I stick with the number of 3. With a few exceptions, kind of optimizations, which we'll see. So, the idea is we can encode everything in the number of 3 tuples, but some things like data streams, numbers, images, videos, audio, and so on, if you would try to encode all this in triples, you would end up with a huge messy graph which is mostly composed of linked lists or something like that to emulate the idea of sequences. And you would do it exactly the same way we humans use to do, like a number. You see each individual digit, and each digit is just a linked list of these digits which make up the actual number. And you don't want to do this, because it's just very messy to interpret numbers in this way. But we still have the way to do this in a graph. And this kind of gives us the possibility to just interpret it as an optimization. Obviously, we want also to do different sequences, not only of digits and so on, of arbitrary symbols. And for this, we only have, we also have the idea of namespaces, which I will introduce in a second. 2 other optimizations are not that important. Right now they are not implemented, but they can be done. Is like if you find pieces of a graph which are very similar to each other, you can compress them and reference them instead of explicitly saving them. Okay. Any questions so far? Everything clear? Okay, thank you. So, nice things about graphs is you can do reflection and meta description of the graph itself. For example, you can do encoding, and the encoding of the data you want to encode can be expressed in triples itself. So you can do a triple which says, okay, I have some symbol, and I attach some data to this symbol, which is not encoded in triples directly, but can access via triples. And I can also make a triple which says, okay, the encoding of that data is UTF-8, for example. So everything in the graph and the graph itself can be described by the graph. Also, a nice property to have is paradoxons. So you can express things which should not be possible. And this is, for me, the sign that it's quite powerful as a construct. Because many constructs cannot express paradoxons. So, probably the most complicated concept is namespaces. But the idea is quite simple. You have these isolated graphs of triples and symbols inside them. And each symbol has an identity which belongs to one namespace. But triples can go over multiple namespaces. And namespaces allow us to do context isolation. So we usually have the problem that graphs are very messy in the sense of you can't just pick something out and ignore the rest. You always have these connections to all other things. And you also don't want to do hierarchies, because in hierarchies you would add on these sequences in the end. So the idea of context isolation is that you can do modularity, distribution, package management. You can use it for security and robustness. You can use it for temporary workspaces, caching, and so on. And another thing which I think is kind of gone lost, the original POSIX idea was everything is a file. So that we only have one interface for all the things we want to do with information. And a very nice feature of file systems in POSIX is still mounting, but nobody really uses it because usually you don't want to write a file system driver for your application, and nobody would allow you to install such a kernel plugin on their computer, even though it's quite useful. And the idea here in this project is that this concept of mounting of virtual subgraphs, which are computed right at the access, not stored, this should be so easy that you can do it all the time. There should be no entry boundary. This again gives us possibility of transparency, so you don't know whatever is calculated as you access it, or which is permanently stored. You can do verification. You can show hardware devices inside the graph, so you know that probably from POSIX. And you also can do induction of infinite sets. You can, for example, have a namespace of the natural numbers, which is not materialized, but still every natural number can be accessed in it. And finally, the last and most important point, I think, is version control. Because I figured out one of the biggest problems of graphs and working with graphs is that we don't have any kind of version control. So usually we end up being alone in our work, and we cannot merge or fork or cooperate with others. And virtualization here gives us the possibility to do version control, because we can make namespaces which represent a graph of a certain version. And we can check out multiple versions and multiple namespaces and have them coexist with each other. This also allows us to do kind of transactional memory and have the feature of that usually we only, as programmers, think of version control as a tool to help ourselves develop with. But what if the actual program can use version control to handle problems of concurrency and kind of use it for scaling over huge networks? Because in current systems we have to explicitly think about these problems, like the synchronization mechanisms and so on. And with version control we could have a way to automate this. But it's still far away, and that's just an idea. I will kind of explain more about it in the end. So far we had the concepts of symbols, triples, the optimization, data streams, and namespaces. Now a little rant about technologies, how they are today, and things I changed in my system. So first of all, there are no bytes. Everything is calculated in bits. I mean, it's a very nice property that we know that the least amount of information, discrete information you can have is a bit. So why not settle for it? Why go up and use 8 bits as the smallest count? I don't know. So, like I said, everything is done in bits. Also, big endian, as you can see, it's not symmetrical to little endian, it's something else. It has one more term inside here. And yes, this actually has to be realized in hardware. This consumes a little bit of power, which is not the actual point. The biggest issue is that you have to convert between these two all the time, especially if you're doing networking. And that is kind of annoying. Probably costs tons of energy, which I've just wasted. So if you ever program anything, please use little endian. Yes, the next thing is data types versus encodings. Most programming languages confuse these two. Like they say data types all the time, but they actually mean encodings. And why is there a difference? Because encoding just means the way you actually store things, information, represent them in symbols. And data types is how they interact with each other. So encoding, for example, is decimal or hexadecimal or binary. And the data type is natural number or integer or real number and so on. But you can store a natural number in decimal or in hexadecimal or something else. So these two things are completely different things, and they're often confused with each other. And the last rant is about semantic web. You might probably have heard about ontologies and triple graphs and the EAV model. And semantic web was the idea to do this to the entire internet. This was an idea even before the actual web as we know it started. And the original plan was to do everything in a machine-readable way, and then construct the human-readable out of this. It kind of failed. You will still see some projects doing this. For example, Wikidata is kind of in this direction. But it has many problems. It's very inconsistent. Semantic web, for example, has not just one type of symbol, but there are different kinds of symbols for different use cases, and you can't put them in each place of a triple. You have to be careful with this. And there are unnamed symbols which you cannot identify from the outside and so on. It's really messy, so I decided to do something new. Starting with this idea of ontologies in the LLVM model, but inventing my own ontology engine and system on top of it. And so far, I think I've been far more successful with expressing different techniques inside this model. And the last part of transport is this quite curious pyramid, which often changes names. So this is my interpretation. You might have heard of something like data, information, wisdom, enlightenment, whatever. I try to stick with these terms because they are far more intuitive. So, if you think about computer systems, we always have this gradient of things which have to be done by either the machine or the human, and we can shift the boundary where we start as a human being. And for example, if you have an image file, and you start with a USB stick, this image is encoded on the stick as some kind of voltage in digital ways like high and low voltages. So this is the data layer. Here is only a stream of symbols, which are meaningless without the correct interpretation. In the next layer, we have information. And this is the interpretation of these symbols. It's an abstract idea. You cannot represent it in the physical world. But it's still important as a hub for all the other layers. And in this information layer, for example, you would know the colors of the pixels inside the image, the decoded image. On the next layer, you have the strategy. Strategy describes how to do things. For example, how to decode or re-encode the image, how to change the color, and so on. Or how to detect things in the image, like object detection. One layer above is the reason. The reason is usually not needed, but it can be, or it's usually done by humans, so it's not needed inside the computer. But our current research goes into the direction of trying to give machines an understanding of reason. So why did we choose this algorithm rather than that? Why did we encode the image as in PNG and not as in JPEG? Because PNG is more suited for artificial images, and JPEG is more suited for photographs. So this would be the reason. And the last layer, which we always do as humans, is the purpose. So the computer does not know why it's doing the things it's doing. What's the end goal? What's it's trying to achieve? We have the utility function. So we are measuring how good this thing is doing its job. And this would be the last step if you want to complete the automaster system. So, like I said, this would be, for example, a USB stick. This is a database or a file system. This is your operating system and the executables in it. And this is usually done by humans. And why I'm showing you this pyramid is because I want you to give an understanding that we can't possibly change where we place this line and where we cut. Questions so far? Okay. So, next thing is the toolchain and user interface. One thing which always bugged me about programming is text. Like, usually we don't even notice it because we're doing text all the time. But if you look in other domains, for example in design, you will see that most people don't or are not that crazy that they would try to For example, edit an image pixel by pixel, or in hexadecimal. Instead, they use tools. They use tools which kind of reinterpret the idea into suitable ways for them. And this is the idea of projection editing. So, for example, a color picking tool. There are many ways to do this. So you have probably seen some of them. There are also text-based approaches, and there are also approaches in different domains like RGB, HSL, CMYK, and so on. But the idea is all of these have one internal representation which you don't know, and you don't have to know. It's irrelevant. You only want to change them in a suitable way for you. And in programming currently we are not doing this. We are always looking at the internal representation directly, the text. And the text defines what we are doing. This also means that we have large disadvantages because, for example, you cannot change the syntax of a programming language after you have released it that easy. You can only add features, not remove one, because then the entire source code base built on this language would collapse. So if you add another layer in between, you get the chance to change the internal representation and separate the idea of what you want to do with the way you are doing it. This is, I think, very important and could help a lot in software development in general. Okay. So, one more thing about projection editing is that you can't really kind of know what you're doing below this layer. This is the problem. This also means you cannot make accidents on purpose, for example, to show off some kind of mistake, error you could make. The system always forces you to stay in the valid domain. Another problem is that the bijection not necessarily works that well. In this domain it's very easy because there's only one color for one hexadecimal representation and the other way around. And in programming we often there's lots of information we accidentally encode and which we humans need even though they're irrelevant to the compiler. For example, the decoding style, the white spaces, and so on. All of this information we use all the time, and especially the order, the sequence of the methods, for example. We use it to orient ourselves inside the source code. But the compiler doesn't know about this and doesn't want to know about it. And if you would do projection editing on top of this, then you run into the problem that you have to reconstruct, for example, geometric layout of the source code in a meaningful way for the human. Because you all probably have seen machine-generated code, which is usually kind of unreadable. And so the idea is you can still do text on top, but it does not need to be text. You can do graphical programming. You could be as crazy as doing auditive programming using sound, tactile, whatever you want. You can do multiple syntaxes and multiple text representations. And so you have to create the freedom of choosing your own interface to the programming language. And you don't have to, you're not forced on one common. And the internal representation is entirely a graph inside. And we will see about that, how that works. One more thing is representation. So I've found 4 ways of doing representation so far, which are the hypergraph, the voxel, aggregated in tables. You probably have seen tables. They're the easiest. So you just write a huge table of 3 columns down with all the triples and symbols inside them. By the way, red, green, and blue stand for entity attribute value inside each triple, and black dotted lines are the same symbol. So in the hypergraph representation, you see each symbol only once, and this line between these symbols are the triples. In the voxel representation, you have a cube, and each point is either set or not set, which means there is a triple of this EAV coordinate or not. In the aggregated, we have merged all the triples with one which share the same entity, which I find the most pleasing as human. You'll see in a second why. And the table is the way to go for database systems, usually. Okay. So, I'm going to do a live demo now. This is the IDE I developed for graph editing of triples. It's written in JavaScript and HTML. The idea is that you here have a space where you can easily find symbols you're looking for via text input. So each symbol can have a data stream attached, and this data stream can be a string, and by the string we can find the symbol, because else it would be really hard to find anything in a huge graph. For example, we could look for the encoding. So you see I can do arrows. It's a fuzzy string match. What do we have here? Can you read it? Mm-hmm. Okay. The idea is this is one symbol. It has two aggregated triples, which are these two. So on top of here we see the entity. On the left we see the attributes, and on the right we see the values. What does this mean? Oh, yes, on this left here, this is the namespace. So the symbol currently is in the namespace basics. Kind of the standard library. What does this mean? This means that UTF-8 is an encoding. And it also means, this is the reflection part, that the string UTF-8 is encoded using the encoding UTF-8. And you can see this connection here. So all the connections are now rendered using these kind of wires, which you can also drag and attach to something else. I think I have prepared a small, yeah, that should do it. So, when you're doing projection and editing, the nice thing is everything updates as you do it. It's like live programming. Here we have a custom encoding, which would represent a struct in C. It has two members. It's a composite. The first member is a 2's complement number, and the second one is a floating point number. And can now add another symbol in my experimental namespace. Call it test. It's now encoded in UTF-8 right now, and can just change the encoding. And now it's obviously garbage, because the string test is now interpreted as a natural number, and there were no bytes or bits left for the floating point, so it's undefined. I can now change this content, store it again, and we get it interpreted, this bit stream, as this new custom encoding, which can also modify. For example, I can say I want to interpret this floating point number as a 2's complement instead. And you see it instantly updated. So it now interprets this instead of floating point number as a 2's complement. And in this way we can change the entire graph. It also supports undo, redo, and so on. And the idea I want to show you here is that we can write user interfaces which actively support the user in changing the information we actually want to change, not the representation of information. So far, so clear. Okay, top.
Can you compile this somewhere?
Yeah, we will get to this in a second. So this right now is just a database. It just stores information. In the future I also want to add a version control so you can share these graphs with other people and work on them together, like Git. So the idea now is to not only represent information in this style, and then have a boundary to some other application which has to kind of reinterpret them in the usual way and process them. But you have the processing system inside of the system directly, like callable procedures in databases, for example. Which brings us to the next point, processing. So another thing which bugged me about processing is that we usually do DAG stack kind of software development. So we start with some set of primitives, and then we build on top of that layer and a layer and a layer. And these layers are usually only allowed to go downwards, and sometimes they skip one layer and so on. But you have to define these primitives in the very beginning, and you cannot change them afterwards. Everything depends on them. And also this is the interface to the compiler usually. Instead, what we could do is do graphs. So some operators, or functions, whatever you want to call them, procedures, use others, and they use others, and they use the first one again. And we only have to break this cycle at some position, but it doesn't matter where. You don't have to think about it while you're writing the program or structuring your program. You can change it afterwards, and each compiler and each target architecture can choose a different set of primitives, which is really powerful, as I imagine. Okay. So the idea how to program is these are the basics now. You have operators, operations, operands, and carriers. So operator is like a procedure or a function, which has a set of inputs and outputs. Operand is a point on the boundary where you pass information through. A carrier is the thing that actually carries the information, as the name says. An operation is an instance of an operator. And, as we will soon see, the operation can also be the operator itself, so you can implement recursion and do iteration this way. A lot like functional programming. To the naming, so things which are on the left boundary are called inputs, on the right boundary are called outputs, and from the carrier side of things, the left is called source and the right is called destination. Why this distinction? Because here you can see, for example, output can be a source and a destination. Okay, so one more thing we need is the constant, because we have some way, we need some way of pushing information into this graph. And we don't want to pass everything as parameters at the start of the program. We want to define information inside the graph right away. And this can be done using constants, which are one extra concept. Also, operands actually don't really exist, they're just an idea. Carriers find their way to each other by a tag, an operand tag, which you can imagine like a collar. And if one carrier has the same destination tag as some other carrier source tag has, then the information will be transported over this operand. Also, obviously, only one destination can feed multiple sources, not the other way around, because here information is replicated or copied, and the other way around it would be unclear which information token would go which way. So, let's start with a simple example. We all know it. This is Fibonacci. As you can see, this on the right is the AST in ASCII art. And these two are essentially doing the same. These, like I said, are only representations, syntaxes. You can add a lot more programming languages with different syntaxes, but they're all doing the same. And the problem of ASTs and sequence system hierarchies here, you can see, for example, is you have to replicate different points of this graph all the time, because there's no other way to connect things. You can only do or connect things by putting them next to each other or inside of each other. You cannot define a connection of this and this over here in a meaningful way in the text representation. And you see this in the tree as well. You have to write this x multiple times in the tree just to explain the connection between these points. And that is what we get from the graphical way of programming. And by graphical, I don't mean optical, but instead graph-based. Okay, so this would be the way to do Fibonacci in my system. Yes, I know this looks a bit overcomplicated. I will explain why and how this works. We start here with some kind of input. This is our x. We don't need to name it anymore. And the variable name x is just a comment for us humans, but the compiler doesn't need it anymore. So we then compare it to the number 2, like we did before. So we evaluate a Boolean for the condition of the if. And now we have two kind of lambdas, which are encoded in constants and put into this if. So if this condition here evaluates to true, this block will put inside here and just push the value right through without changing it. And if this condition here evaluates to false, this bigger block here will instead put here and then do the recursion and the actual Fibonacci calculation. Again, these Fibonacci recursive operations will execute the entire thing again. So it's recursive. And this is done in eager evaluation, not lazy evaluation, but we could also do the other way around. If you're wondering, the two concepts are actually quite equal powerful. The only difference is if you can encounter infinite recursion in logical ANDs or logical ORs.
May I ask you a question? You said operations are instances of
operators.
Of operators?
Yeah.
So is your Fibonacci rec inside the two small ones? Is it operations?
This block here is called the operation. The operation is a placeholder for the execution of an operator. It's like a function call.
But is it an instance that you can look into again and you see the same thing again, or is it a reference to the outer representation?
In the representation, it's just a reference, but because it's projection editing, you could write a program which would allow you to open this up and see the recursion.
Okay.
To kind of follow the alias.
Yeah.
So, this is what LLVM thinks Fibonacci is, which is quite similar, in fact. So we can map these concepts more or less one to one. An operator is a function or a basic block. A carrier is a virtual register. And the only thing we additionally need is this phi node here, which then reconnects the different branches and control flows. So one thing which is nice about this concept is you can define control flow in data flow. You don't need any additional construct to do this. And instead LLVM does. So we have to kind of change the graph the other way around to explicitly model the control flow here. So in LLVM, we obviously again evaluate the expression, and then we choose one of these paths, this or this one. In the end, only one was taken, and we merge back into the main function, as we know. Okay. Yes, I think this is the time to show you what the compiler actually produced from this Fibonacci example here. So each operator is compiled into one function, LLVM function. And yes, the names are mangled because all of these operations, they can carry runtime values and compile time values. Everything is a kind of const expression by default. And you have to explicitly mark runtime values as such. So everything has its own identity at compile time. And things can be evaluated as if they are compile time the same way as if they are runtime. So there's no more difference between those two. Everything that cannot be right away evaluated at compile time will be postponed to runtime. So these are the blocks again. You see here our if, which just calls the then or the else operation. And these operators are then defined below. It then just passes the value through, and the else does the actual work. Also, the primitives like subtraction and addition are operators too, like I explained. We can exchange them, and we can also take, for example, the address of them, which is not possible in C#, for example. Okay, now we can compile this with the LLVM optimizer and compare it to a C implementation of Fibonacci. So this is what we get from C. I think it's clear so far what it does. And this is what we get from my compiler. And as you can see, the only difference here is the order of these two operations. Because in the C style, we actually explicitly defined the order and the compiler didn't change it, just accepted it. And in this style, the compiler has the freedom to rearrange the operations right away. There's no order definition other than the dependency of carriers. So if you want to explicitly order things, you have to connect them via a carrier which does not carry anything, just to make a constraint of the ordering. This allows you also to do memory accesses and order them in your program.
Can you go to the slide where you show the phi node? And this phi node, how does it know which one of those, the red or the green, how does it know? Is it connected somehow to the if?
Yeah. Oh. So this outer block, the if and the phi node are one LLVM function in the end. And it contains the basic blocks of these two operators. These are inlined.
Why do we need an if? Why don't we connect directly the condition to the phi node? Oh, you don't have. If you think it's for the end, we can also not answer this.
Yeah, I think we do it then. Yeah. Okay. So next thing is different transformations we can do in this model. A thing I noticed in programming is that you don't really have a way of explaining how information goes in or out of a function. There are multiple ways of doing this. One way is to define it as parameters. Another way is to call a function which then retrieves the value for you. And you could imagine a programming language which also defines the outputs as parameters. And obviously what we are doing all the time is passing the output to some kind of call, which then passes it on to the actual callee. Yes, this in fact is really easy in my system. Like you only have to cut the outer boundary and interpret it as two operations. So here this input becomes an output of such a virtual operation, and the output becomes an input of another one. And it's a really simple graph transformation. You don't really have to think about this. There are some other nice graph transformation. I think the best one is that you can do capsulation and inlining for free all the time. Like you can cut every point of the program, every point you want, and define a boundary, take the subgraph out as a new operator, and you can do it the reverse way. You can inline an operator into something else. And you can do both. You can visualize these using projection editing and just show the user an inlining without doing it, or explicitly materialize this inlining. And another thing you often want is bundling and unbundling carriers to avoid the chaos in our source code. So we can have operators which do these. And in fact, they are very simple to do in LLVM. You might have wondered how I do multiply return values. Well, this is how it's done. Very simple. For example, this is division, doing the actual division and a reminder. And I put both of them in a tuple structure, then pass this to the outer function, and extract them back again. This is done transparently by a compiler. You don't see this. Yes, and probably my favorite feature is code induction, injection, however you want to call it, and self-modifying code. Well, it's debatable if you actually call it self-modifying, because it's modifying what's executing next, not itself. It's like a train which builds its own railroad. And so the thing we can do is we can either pass the operator we want to execute in an operation statically using a constant, but this can be hidden by the projection editor. You don't have to see this mess all the time. Or you can have a program which generates a program and then executes it. And the compiler will do this transparently in the same way. So you don't notice which of these two ways is actually happening. You can define things which the compiler should not touch, but postpone to runtime if you want, or you don't want the optimization step, because you want to save memory, for example. And this enables us to do heavy meta programming. So, for example, you can do all the template and const expression magic using this trick, because programs can manipulate their own representation and then still be executed and compiled to the point where it's possible. Questions so far? Okay. Yes, as a summary, like I said, not only multiple input values, also output values, so everything is symmetric. The operands are unordered. Usually in programming languages we order them, and the index of a parameter matches then the index of the argument. Operators, or which operator is executed by an operation is defined by the value passed through an input operand, which enables this magic trick of metaprogramming. And control flow is interpreted as data flow, which also means there's no early exit and no variables. Why no early exit? Because there's no sequence anymore. There's no early and late. There's no definition of time. So usually if you, for example, return in the mid of a function, you implicitly discard all the other instructions behind this return. But in such a representation where you have a DAG, we don't have a before and afterwards anymore. Not a clear one, not in all cases. So you have to explicitly define which operations you want to discard. And this, in fact, is the same as structured programming, and it's doing an if and an else operation. Yes, you can use void carriers for additional ordering constraints, and you can also use carriers to do a total order in the end and do a continuation sequence, like explicitly defining the program counter and how it's going through the graph. And this has to be done by a compiler at the latest stage because it has to schedule the instructions. And in fact, I think this representation can be used for all stages of the compiler. As far as I'm aware, currently compilers use different representations for different stages, and they have to kind of convert them in between. And this is no longer necessary. So you can just add more information at each stage, and you don't have to touch the other stages. Okay. Yes, like I said, everything can do automatic type deduction. Currently, the thing I do not automatically do is in the case of recursion, because you don't know what you will return if you don't know what you get in the beginning in a recursion case. So I still have to write an algorithm to do this. Currently, the human has to give a hint that in fact the return value will be equal to the input value. But I think it should be possible in general to automatically deduce every type. And also you can do dynamic typing at runtime, because you can just pass symbols, and symbols don't have any type. It's stack typing. The symbol just pretends to be of some kind, and if it's accepted, then it works. Yes, also everything is constant expression by default, and you have to explicitly mark runtime values. And operator boundaries are no longer sync fences or barriers. So usually we think of these boundaries as a sync fence. So if multiple values go in, we think that the execution will only start if all values are ready. But of course there's inlining, so this does not need to be. And things can be executed independent of the other operands, which are already available. Yeah.
In this last slide before the summary, you had this dynamic execution of operation.
Mm-hmm.
So this means you ship the whole toolchain together with the executable in the end, or?
Yes, this is a very interesting question. How are operators represented at runtime?
Yeah.
And how are they dispatched?
You will show it later, or?
No, I can explain it right now. There are, I think, 3 ways of doing this. One is to actually just compile it statically, which we see here. Another one is, you know the exact data types and encodings at hand, and you can do a function pointer. If you...
Please say it again, functional what?
Function pointer.
Function pointer.
Pointer, yeah.
Okay, yes.
But you want to generate the code at runtime, or did I understood it?
Well, it depends. If you know already what you would be generating,
Okay.
which the compiler can't figure out, then it can generate code for this and just place it in the runtime, and the runtime will then select one of these.
Okay, but it should be easy to make an example where this is not possible.
Exactly. And in this case, if you don't know anything about what you want to execute, you obviously have to do a just-in-time compiler or a dispatcher in some case. This can also be an interpreter, obviously.
Or interpreted, right?
Yeah.
Mm-hmm.
And in fact, my compiler is an interpreter and compiler in one. So there's no real difference. All these operators are, in fact, evaluated as like a functional programming language. So they're cached, and the code they produce is also cached. If I call an addition twice, it will use only the machine code of the first execution. So, the project on my journey so far, I started in 2014 with a C++ implementation of the ontology engine. And by the way, obsolete means it's been replaced by another sub-project. I implemented the ideas of symbols, triples, and data streams. Namespaces followed way back, I think, in 2017. And I started the documentation. In 2015, I did the first CLI. This was my prototype of an user interface, which grossly failed. Completely unusable, in my opinion, right now. And I did a human-readable language of graph representation, which also did not work out because of all the problems we have with text. And these are only made worse by the fact if you try to convert a graph into text and then push this into a subversion or Git, the order will change every time, or can change. And people can use different styles of representation of graphs. And this is really messy, so I need a version control system which understands graphs directly and not via some kind of text representation. And I implemented a very classic execution model. It was a register machine, which could also compile source code. And I only later on discovered this idea of data flow-based graph models and execution. Yes, in 2016, I did my own memory management system for the entire thing, and standalone, so I discarded all dependencies to other projects, including the standard lib. I started a web-based visualizer, which you have seen. I did an experiment with WebAssembly, showing that you can, in fact, compile the ontology engine and then run it in the web using the visualizer. I did some interfaces like TCP, a fuse, emulated file system. So you could use Symatem and the ontology as underlying concept for your file system. And I started a side project called Unikernel Experiments, in which I programmed a bootloader and a unikernel for ARM64 development board, just to get a feeling of this and how much can be done. In 2017, I had this idea of the DAG execution model, which took quite a lot of time to develop and get right. I also did many other stuff like data containers, compression, encryption, and so on, some utilities, just to figure out if these are possible in this concept. I had the idea of namespaces, which also took quite a lot of time to just get right, in the way of there's so many alternatives what you could have done instead. But instead of just trying to get stuck at some point, you have to move on. And so I decided for namespaces, which to this point I still think are right. So there was also a binary initialization ontology encoding, which I'm still using. But like I said, these are problematic for version control systems. I now have an JS engine implementation and the ontology editor. And since the beginning of the year, I now also have my LLVM from the prototype. I do plan on implementing my own compiler at some point, but LLVM is good enough right now. So, the sub-projects and the state of the art. Obviously, I have documentation and website and some other meta stuff. This was the classic runtime environment, the ontology engine I talked about. Yes, written in C++, it means it's C with some C++ features like templates and references, but not the standard library. Which I can compile using WebAssembly and run it in the web. Also, the compiler currently is JavaScript based, but later on all of this is supposed to be happening in itself. So this is the next big step of re-implementing all of these ideas in themselves. Eat your own dog food is the acronym here. And the user interface should get also a programming editor and projection editor and a version control. This is, I think, the most important step in kind of spreading this idea and make it more accessible. Before I don't have these two, it's hard to use this. Yeah, like I said, these are the future goals of the project. First of all, the projection editor, re-implementing the engine in itself. Drivers for namespaces and mounting of namespaces. Currently, I only have the induction of natural numbers, but I want to try many other kinds of namespaces and programs which run drivers for namespaces. I think this will be very fun. And this will then ultimately enable version control to be done in namespaces, programmatically and transparently. And in the end, I hope to, like I said, compile itself in itself and also make an kernel for this thing so it can run standalone. Because as you've seen, all of these ideas are quite far away from what we currently use, and adapters to the system are messy. They don't really work fine. So I want to try to do everything in itself. Okay. I think that should be about it.
So good.
Yeah.
Yeah, the obvious question is, how are you using LLVM now, and what is not working for you in
Exactly.
LLVM? Why do you want a separate compiler?
Why I'm using it right now is because I think it's
Yeah, and how?
it's the easiest way to get something compiled at the moment. If you just want to start with something that is compilable, so I can generate an executable which then can implement itself. I think it would be harder to do this in other projects. So this is the reason I decided for LLVM. And what's bugging me about LLVM? It's still very, very close to the actual text representation. And LLVM kind of is based on the idea of compiling C, or C-like languages. You can see this in many corners. For example, there's only one return value, or other stuff that, for example, meter information and debugging information, it's all C. C style of lines and columns and so on. There's no way to attach meter information in an arbitrary way and so on. So, and the other thing is I want to learn about designing compiler from scratch, and I also want to try this idea of having one representation throughout the entire process and not changing the representation in between, just adding information.
Can you repeat this last sentence?
Yeah. I can only, or in LLVM and in most other compilers, we change the representation, or we transform the source code multiple times in SSA and in DAGs and in sequences and in binary encodings and so on and so forth. And I want to try an approach where I only do one representation and I add more information in each step and each stage of the compiler, but I don't change the entire representation in itself, which would allow us to kind of have more control over debugging inside the compiler, because you could track things from the very beginning to the very end. They could keep their identity to a certain extent. Obviously, at the end, you have to do a code emission, and then you have to ultimately change it to binary representation, but that's the last step, right?
It would be great to have an example of this. but thanks, yeah.
Question about typing in your system. So you have also symbols which are variable types, meaning you have some kind of memory management in the background, or do you have pre-allocated everything that would restrict you to non-variable length types?
Oh, yes. In fact, I thought a long time about how to do encodings and how to express them in the graph. And these encodings, they are capable of doing variable length and static lengths. And they are also capable of new ways which you don't currently have. For example, I can do inlining of structs, of dynamic size structs. You can't do this in C. In C, you're always limited to the size of a struct. You have to know it at compile time. If you do inline one struct and another, and you want the size to change, you have to use a pointer. And in this system, you can actually write them exactly behind each other.
Yeah, whatever.
And you can have a variable length in that way. And it's implemented via the data structure of so-called ropes, which are a kind of tree which enables us to do log n insertions and deletions in a sequence.
Okay, that brings me to my actual question, which is in your graph, I don't know how you call it, I would call them patch cords, cables, carriers, you call them?
Do you mean
the connections between your object?
Do you mean in the ontology? So
in your visual representation?
These are the triples.
Yeah, the graphs. Okay, and so when you connect an output to an input, basically they are the same. Do you generate code when you have multiple types going through there? Do you analyze this and generate code multiple different multiple code paths for each type, or do we have a variable variant? Do we have some kind of union style container that you send through it, and which one of those?
So the question is whether or how the types of runtime values are encoded at runtime, and how
at compile time. So if you have a graph and you have types going from one to another, from one location to another location, let's call it like that. If there are multiple types to be carried through there, you have to make either multiple paths. Or
yeah,
you have to either generate multiple paths for the multiple types, or you have to generate some kind of container that can be understood by both endpoints.
So you're wondering, for example, if this Fibonacci recursive is taking an integer
Float
or a
versus
float.
integer, exactly,
Yeah.
or a list of floats, and so it can then work on a list of floats.
Yeah, this could easily be vectorized. So what the compiler does, it instantiates every type like a template, and all these templates are cached.
So you have different code paths for each.
Exactly.
Cool.
And you also can do arbitrary symbol, and then this has to be evaluated at runtime.
Yeah, of course.
Yeah.
But when possible, you do a different code path for each type.
Exactly. Yeah. You could obviously also kind of try to program it and decide each time you hit such a value, which could have multiple encodings, and do this at runtime to save memory if you have thousands of different.
So just wanted to know what path you did choose.
This is the standard.
But that means you have to, excuse me, you have to regenerate different code for different encodings.
Yeah.
Doesn't that go against one of your rants earlier, when you said there's a difference between data types and encodings? And now you could have different encodings for the same data type, but then you'd have to generate different code.
The rant wasn't about the technical aspects of data types and encodings are both necessary. It was about the distinction of these terms. That we usually confuse data types with encodings.
Yeah, but this is a mistake that you're likely to make here too, right? Because you'll have one data type, but then if that data type has different encodings, you produce different versions of the same code for different encodings.
That's the technical side of it.
But they all match the same data type, right? Is that?
Yeah.
Yeah, that's all consistent in your.
And then you have to have a state machine that actually keeps this whole thing in sync.
Which synchronization?
You can come up with in between the different code paths, because if at the moment you have flow control messages in here that could trigger specific memories and syncs and whatever, and then you come into this state. One step back, is this whole thing stateful? For example, could I completely restore the graph at one point in time? Could I stop it?
It's deterministic, so you can re-execute it. But it's vendor specific, so if you execute it twice at the exact same implementation, it will result in the exact same order of doing things. There's no random aspect to it. But different vendors could, in theory, do different implementations which could change the order, as long as it does not change the behavior of the program. Did I get your question correct, or?
Yes and no. The thing is about these two different generated code paths for similar data.
Oh yes, one thing about, I think this is the mangling. The trick in this mangling thing is that the operator, if you want to execute an operation, is one input of this operation. And it's also encoded as part of the template instance. So all these different template instances share the same operator, and they know this by the mangling of the function. So the compiler knows which operators yielded which functions and which instances of encodings were used in the.
So we're working on the same data.
They're using the same representation. Underlying code structure. Yeah.
Underlying code set, but underlying data. So when I come with a different encoding into the thing, in a recursive thing, when you feed it with different encodings, will I get the same value? Is the underlying data itself that represents this the same? So Does it matter if if it comes with one encoding, then the next one is another encoding and whatever?
The encoding cannot change because each code path statically is defined for one encoding. And in a recursion case, this stays the same.
Okay, so
I think
So
I
you
have a
would
good
have to explicitly
okay,
change the
you have
encoding.
to explicitly change the encoding,
Yeah.
so you duplicate the code path for everything, and then you have unconnected code paths. Okay,
Yeah.
thanks. Now,
I think I have a good example. Can you go back to the Fibonacci
Mhm.
example? If you, for example, if the user, the program plans to, for no reason, to cache the value it's calculated for an input, for example. So you would make a wire from the input to somewhere, and then say, I don't know, have a module that is called cache, and it has a table of inputs matched or mapped to outputs. And then you have this module, like one version for an integer and one version for a float, or for different encodings of an integer. Like, and then would the cache be shared for all of these modules, or would it be
thanks.
in every instance? And that was also the question that was like, I wanted to ask for the internal modules here. Is it like a reference to the outer one, or is it its own instance?
Okay, what we have to distinguish here is the way it's represented in the actual code.
Yeah.
It's just a reference, because we don't want to do infinite instantiations
Yeah.
of this. Okay, but the idea of the execution model is that each is their own new instance, each depth of the recursion level. So,
Okay.
which in fact is independent of the other one. So if I were to change, for example, by self-modifying code myself, this would not change the outer one.
Okay.
And if you have this example of caches,
Yeah.
you would have to explicitly define as a user which data or which storage address to use,
Okay.
and thereby define if these collide or not.
Okay, so you had to define the data type that is stored inside the table in the cache module, you mean? And this would restrict the whole module or the whole operand to this data type.
You could automatically generate converters.
Yeah, yeah,
Yeah.
yeah.
You would have the cache as an input.
So you could say the cache. You could easily generate a cache that could hold and sync
Yeah.
data types.
But it will be different if you see one operand in the visual representation, and then internally it's different caches because it's
Yeah.
different data types. This would be confusing for the guy who's using it.
Yes, in
Which
fact-
makes your all the way through a tagging of errors and up down to the thing a little bit more difficult, because you could have an error in one representation but not in the other representation.
Yes, this is true. You can have different paths, and there's no guarantee that you discover all the paths and what could go around these paths.
Do you? What's the biggest thing you built with that so far? Like, can we have a look?
It's a small screen, probably.
This is a small screen. I don't know what your standards are.
Yes, it's absolutely true. The graphical representation takes kind of more space
Yeah.
than what you're used to in text representation. And this is probably one of the biggest disadvantages of my current system. And I'm still working on trying different layouts and so on, and also auto-layouting. For example, this is done by me. And in fact, this in the projection editor, this has to be done in the machine. But there are ways to do auto-layouting of graphs. The nice property is that this is a DAG, so you can do a topological sort of the entire program, and this will solve the most layouting problems. Because data always flows from left to right. There are no cycles in this.
There's no loop.
Well, a loop is implemented by recursion. And recursion, in fact, can be shown by spreading the graph, not by drawing a cycle.
Sorry?
So if you're doing a loop, you don't have to draw a cycle. So usually in LLVM, you would draw a cycle, yeah?
Okay.
You would connect
Full
this
graph, yeah.
back again to the beginning, right? You can also do, obviously, recursion. But in my model, there only is recursion. You have to transform all iterations to recursion. And this has the nice property that always stays at DRG. All the control flow, all the data flow always goes from left to right. And it makes it easier to lay out this automatically. And like I said, you can also do a text representation or auditive representation or whatever of this concept.
Yeah.
Mutual recursion or what? And mutual recursion is fine as well.
Mutual means?
Well, you have one block where you call, there's fibreg 1, and then you have fibreg 2, and fibreg 2 calls fibreg 1, and fibreg 1 calls fibreg 2.
Yeah, you can have bigger cycles, yeah.
But
The number of steps in a cycle doesn't
don't
matter.
have cycles. But you don't have cycles, that's the whole point.
Yeah. So you can obviously go multiple steps inwards. There's nothing stopping you from doing this.
And so
Is that fine?
can you have some kind of reference? Can you mutate the data? So if you have, say, a huge array you want to process, you always need to make a copy of this array, or can you process it in place?
No, now we're getting in the corner of how stateful is this entire thing? Is it functional, imperative, and so on? Okay, so the idea is here that you're not limited to functional or imperative programming. This also, for example, does not make any statements about thread consistency. And you can, in fact, write a program like this one, which is completely stateless, because you don't have any stores or loads here. And you can write programs which do have, and then you're on your own, you have to order them explicitly. And to make sure that this order is correct in your semantics. Because the compiler doesn't know if the ordering of memory access makes sense or not. And if you actually want to change some value, or you're doing it by accident.
So you can.
You can do both.
And how do you represent that in your graph? You have some references or pointers? Or?
How to do? Actually, yes. You can have a data type which is a pointer. You can have an encoding like natural number, and you can pass this around just like any other value. And the compiler doesn't know this is anything special, except if you take it as such and then write a compiler which notices that this is something special. And so to the model, it doesn't matter. You can do memory accesses and operations, primitives for memory accesses, but the compiler doesn't have to know necessarily about these, that these are memory accesses in fact. It's just the operator like anything else. And as an optimization, if you want to do things like pointer aliasing and so on, you can still write a compiler which does notice this and thinks about it.
So let's call them code path 1 and 2 with the Fibonacci recursion 1 and 2 that are labeled here like that. So as we've seen in the code, there is no notion of order here for this at the moment.
It's a partial order, it's not a strict total order.
So I cannot tell if 1 comes before 2 or 2 becomes before 1.
Well, the possible ways is, for example, it could execute this first, the minus, then this Fibonacci, then this minus, then this Fibonacci. It could also execute this minus, then this Fibonacci, and then this Fibonacci. But it obviously has to do these two Fibonaccis before this plus, and it has to do these two minuses for each of their Fibonaccis.
So when we now add a state where that both of them, for example, use, because we just want to store the outcome of the minus operations in a shared state between those two, you have a representation in the graph for that state? Could you do that?
Yeah.
And
So
then
the question is,
the question is, could you then have? Do you have another object that would spawn ordered execution, so that I then know graph 1 will be gone through, has stored this thing already, and graph 2 comes? So
Yeah.
you can order the graph?
like I said, you can do this by adding more carriers which are more constrained to the ordering, to the point where you define an explicit order
Okay.
of the entire program. And you can in fact do something like a carrier which explicitly carries the program counter. So each instruction gives the program counter to the next instruction. And because there can only be such one carrier, then you have a total order of the entire program. And yes, this is done by the compiler in the end. This is the scheduling process or stage, right? So every compiler has to do this at some point. And back to the question of representations, you can do binary representations and you can work with these all the time, like C-structs and floating point integers and so on. Then you have to do the structure and the management of these yourself. This is important because you, or I want to program very low-level stuff like a bootloader, for example. And I don't want to run the entire virtual machine on this thing. Not in the beginning. It has to bootstrap itself at some point. So it can do this in a very basic way and only use these PUD types. And later on, it can still call operators, which then will invoke the virtual machine and access the actual triple graph and use the entire ontology. But this is like a call to, like a system call. Not clear?
No.
Okay.
Maybe not. But I have a different question. Now it's gone again.
Okay, then I will try to elaborate this. The ontology engine you see right here, this is quite complicated program, right? It's an entire database. And you can make, you have a system of doing queries, and also to change this graph and retrieve information, put information back there. Later on also do version control programmatically and so on. And all of these is done by calls to operations or operators which access the graph. But you don't need to do this. This is only part of the standard librarian. This is not part of the actual concept of programming. This is an add-on. The higher kind of data evaluation. You can stick to doing everything in the C style.
And back to the previous question, the question about the big program, do you have an example, another example more than just one function, like a couple of functions, so maybe something a bit more complicated?
So far not, no.
Okay.
Like I said, this will be the next step to re-implement the entire engine. But I have written it in such a way that it is possible. Because, for example, I have set myself multiple constraints in the coding style. For example, how I manage exceptions and so on, which is not covered by this model right here. But you can add it using the measure program. For example, you could write, one concept would be to do more complicated programs, to just generate programs by other programs. So you could have a program without exception handling, but tags which let the compiler know which points can throw exceptions and which points can catch them and so on. And then one operator could inject code into your program while it's compiling it and patch these places which you have previously marked. But you don't have to explicitly do this all manually. And this avoids a lot of chaos.
Okay, so you have patch points for things like handling errors or throwing exceptions or things like that?
You can do this. Like I said, everything is encoded in a triple graph, so you can mark everything with all the amounts of metadata you want to do. You can invent your own stuff, and the compiler will not be upset about this.
Okay.
It does just ignore this. It's just like a comment. You can also use it if you program it to use it.
Okay.
Yeah.
So from a perspective, you got another way of solving algorithms problems that used to be done with high-level programming languages like C++ and LLVM. Now with a more generic approach, like using graphs, using more the natural way of triple graphs like semantic web is doing, and by embracing these more natural concepts, you get a more clear and powerful design, right?
Yes, I think this is obviously everything is turning complete, so there's no gain.
Okay, yeah. But yeah, well, there's a gain. Well, now we talk about it. What is the game? What's the problem you're solving? I'm not asking this right now because when we want to evolve, let's not talk about LLVM. Just LLVM, just a very good tool. But let's think about some problems we have, like we writing source codes like text files. This is one thing, and which is like, okay, we're not using stones anymore. That's fine. But yes, there are advantages. But we are still quite stuck in our paradigms. Like only a few IDEs are using it. When you change a parameter, then it's all the parameters have been changed. So it's not really helpful. So these text files are representing graphs already. We know like the methods and links and so on. So there can be much better tooling. But we have to, at some certain point, we need to jump out of these paradigms, old paradigms. And machine learning is one thing like, let me summarize it like, oh, we know there's an input and an output, and there's some rule in between, but we don't know how it works, so we put in machine learning and we get the algorithm, right? And at that point, the data becomes first citizen, and when the data changes, we need to change also the source code, the algorithm changes. So it's something I learned just yesterday, so I have to mention it, because then the continuous integration will have to take into account the data, and it's getting more and more complex. Another high level, but what I want to do is, let's say we have another new intermediate data language, like that is fine, but it does not solve certain problems. And the main problem to me is I'm a human. I want to speak very easily to the thing that I'm programming, the solving machine, and something comes out very powerful. Okay,
yeah.
And I got questions like, oh, I got OpenBR, like Open Biometric Recognition, and I got Tesseract, which is an OCR, optical character recognition tool, which have got something similar. And I thought, oh, maybe because they don't find the character so well, maybe I can use approaches from OpenBR on Tesseract, right? So let's take a look at both open source codes. It's horrible. I mean, I got a very simple question, right? I mean, more or less simple, but you got billions, millions of things which is just annoying data, boilerplate, things that are not that are hiding the information you're seeking. And I fear we're not going back to the intermediate code. Still, we're not assembly anymore, but it's not solving this problem. It's just a step back. I think in the you try to map all the programming language to a common language, so we don't only have the LLVM languages in some like Java, something else, and so, but we have one thing to solve them all. And now, please keep in mind that the main goal is to attach to ourselves, to humans. So we have to somehow embrace these bigger questions. How can we interpret or how can we solve, go through the source code far easily, or I don't care what search is using or what search being used. I know from some Java classes they're using different algorithm hash map depending on the amount of data. So in this kind, I don't care so much what it should be changed depending on the data. For instance, yes. So I don't write it manually explicitly, and just put it in search. And okay, metadata on that. I really love what you're saying. I don't understand everything, only a glimpse. I get but what I understand is very nice. And still, I would just give you something on your shoulder that these the human things is it's quite correct thing. And if I don't bore anyone, I would like to solve one thing about versioning in graphs, because I'm doing the same thing on documents, Office documents, which are graphs, by the way, also HTML. And to do versioning on Office documents is you define the changes you're doing, because every user is doing the same thing, adding paragraphs, adding text, doing certain formats. They don't do anything like, oh, here we changed this bit. No, you don't do that. You And when you do versioning, the main thing is you want to collaborate. And when you want to collaborate, you want to ask the others, what have you changed? And you want to get the answer to this question is the changes. So the first citizen is no longer the graph itself, but there's a different way of thinking. It's just a sequence of changes. So like the current spot is like you look back to history and you see only the commits, right? Back to the beginning, so the changes. So you might need to define the on a higher level, and again, the higher level it gets, the easier it gets for the human changes. So sorry for the discourse, but I stumbled into change tracking myself, and under redo change tracking is both fully the same. And as soon as you define changes, then it's getting it's pretty easy with these things.
Sure, blockchain can solve that for you.
Pardon?
Sure, blockchain can solve that for you.
Okay. Oh, yes. Okay. Blockchain is blockchain is Yes,
Okay,
counting.
I will try to, I think I had 3 points, I do them in reverse. Yes, version control. Like I said, it's very, very similar to undo redo, and it's all about actions and deltas.
Right.
Yeah. And in the version control system, one of the main points or problems I encountered in version control and automated version control, which I think is the actually interesting part of this, is that there is no way for a machine to generally understand what an action is or how actions should behave. This has also has to happen by a human. Because if you could solve this problem, we would have general artificial intelligence. If a computer could understand if information or 2 patches together make sense or not, this would be artificial intelligence.
Come on, you have a very restricted set of potential commands of adding to a graph. This is not artificial intelligence. This is called Google Docs. But,
no. I'm not talking about domain-specific changes. I'm talking about general changes.
Yeah, the problem lies in conflict detection.
Exactly.
In this whole thing. So
Exactly. So
it's been solved about 50 million times now in 50 million applications, but has always to be done.
Yeah.
It's just a pain in the ass to program.
yeah, exactly. That's what I'm saying.
Interesting. It's always usually it is a valid state to a valid state. So it's the defined. Yeah, it's the transition from one valid state to the other. And I'm not sure if it's here the case, but like in documents, it's the way the user changes something, right? And the intermediate, there's the same problem. We have different syntax like ODF and OXML, and we have then logical blocks. And what you do is you take only you abstract in the graph of logical blocks and do changes on this graph on these things. So, and if you would define this, it should be you should be able to to have a change tracking, wouldn't you? Or some.
This is the idea of the namespaces. So the namespace driver can track all the changes you're doing in this namespace and convert them into diffs or patches, transactions, however you want to call them. And you can then transport this diff to somebody else and they can apply this. And yes, like I said, the tricky part is recognizing what is an action and what isn't, and are 2 actions compatible? Can they be merged? And this has to be done by a program, which has to be written by a human right now. This is the idea of namespace and their drivers, that you can in fact write programs which then help you to recognize actions and to sort them and categorize them.
Yes, I'm just thinking about when we program this current Stone Age way, like a text editor, IDE, something like this. So the current changes are characters, right? Which is Stone Age because we're constantly coming from one invalid change to another. Because unless I finish my statement, I do an auto-completion. So the next age would be you step from one valid to another thing. Yes, somehow it's working. And I would go the way, how does the big brothers, the high-level languages, the programs, how would you go from one valid state to the other? Yes?
So how would programs use this as transactional memory? This is a form of software transactional memory.
Yeah, yes.
Yeah. Well, there are different approaches, but I think the easiest is to actually explicitly mark or think about commits. So you say, okay, this part of the program will read data in from the last commit and output data into the next commit. And then it's doing a transaction, which is consistent. And then it can call the next program based on this transaction. Also, the program can decide to read multiple commits of the same graph in different versions and compare them and so on. So the idea is that by namespaces we give the program access, transparent access to different versions of our graph. And the program can interact with all of these versions simultaneously. And you as a programmer are now challenged to use this in a meaningful way of defining the transactions so that they are useful actions for your user. And yes, you have to also write a program which figures out what can be merged and what cannot be merged. This is the critical part. Tracking the actions, figuring out what has changed and so on, that's easy and applying it. But figuring out what can be merged and what cannot be merged, this has also, or always has to be done programmatically.
Okay, any more questions about maybe the LLVM part of the thing? Or I would have one more. You generate the IR for your graph, like we see it here. What do you use to generate this? Do you use like the C interface, or do you use the API, or do you write it by hand?
I've written my own code emission, which is
okay. So you
written in E6. It's quite simple.
You write text for each of the modules. Yeah. Okay. Any more questions? Okay, then thanks for showing us your presentation. We can talk about all the other questions like in one-to-one sessions or something. Okay, cool.